The goal of this video is to introduce the concept of an infinite series, introduce the notation that's typically used with an infinite series, and just to kind of lay the groundwork for what is the fundamental question that relates to infinite series. So let's start with a definition. So an infinite series is an expression, right, of the form, and I will start by using our wonderful sigma notation. So sigma, which represents a sum, and I'm going to say k goes from 1 to infinity, and then I'm going to put as my summand this expression a sub k. Now we know this expression, we've seen it in the context of sequences, and now we're going to say, well, what does it mean when we put this sigma sign in front of it, right? Well, we know that sigma means sum, right? So for instance, let's say if I were just to think of the terms in the sequence, right, then I would write down the first term, since our index here starts at 1, then the first term would be a sub 1. The second term would be a sub 2. The third term, a sub 3. And then it would go on, and then dot, dot, dot. So those would just be the terms. What does the sigma mean? Well, we know that sigma means sum. So now what we're going to be doing is adding up these terms. We do another one, and then plus dot, 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 right? So essentially what an infinite series is an infinite summation, right? So this is an infinite summation. In other words, it's a sum with infinitely many terms, right? A sum with infinitely many terms, right? That sounds interesting, you know. Who's up for adding infinitely many terms together, right? So the idea is this, since we can't physically add up infinitely many terms, we have to come up with some process or some theory that allows us to make sense of this, right? If I give you 3 numbers and I say add them together, no problem. If I give you 30 million numbers and I say add them, maybe a little problem, but you can still do it. It's still finitely many terms, but how do you add up infinitely many terms? Well, before we write it down, let me use this little example just to kind of motivate where we're coming from. So consider this decimal. So consider 0.3333 and so on, right? Often written as 0.3, and then you have that recurring line above the digits that repeat, right? Well, the interesting thing is this can be thought of as an infinite series, right? Because look, here's another way to write the same repeating non-terminating decimal. I could write the 0.3, so just keep the tenths spot, and then I could add the hundredth spot, and then I could add the thousandth spot. Okay, I'm going to stop saying it like that, but right, you get what I'm saying, right? So we take the 0.3, and then we add to that 0.03, and then we add to that a 0.003, and let me write it one more time without saying it, and then we continue that process, right? So this repeating non-terminating decimal can be thought of as an infinite series, because since the 3's never stop, then my summation here would never stop, right? Or equivalently, it could be, if we write this as a fraction, then this is 3 over 10, and then this is 3 over 10 squared, and then this is 3 over 10 cubed, and then this is 3 over 10 to the fourth, and so on, right? But we know, right, based on our knowledge of numbers, we know that this number, this 0.3333 that goes on forever, is actually 1/3, right? So how do we reconcile that this number 1/3, which is a perfectly good rational number, can now be thought of as the sum of infinitely many terms? All right? Well, this is what I'm going to do. I'm going to define a sequence. I'm going to say, so let S1 be equal to just the first term here, the 3 over 10. And then S2 would be the sum of the first two terms. So 3 over 10 plus 3 over 10 squared. And then S sub 3, so again, let me write this. So this would be, again, of course, the 0.3, and then this would be the 0.33. S sub 3 would be 3/10 plus 3/100. There I am saying it again. Okay, I'm going to stop. And then 3 over 1,000, so that would be just the 3.333. And then S sub 4, 3 over 10, plus 3 over 10 squared, plus 3 over 10 cubed, plus 3 over 10 to the fourth. So then we get 0.3333. So what we actually have here is a sequence, and I'm just showing you the terms of the sequence, right? And then each of these, right, can be thought of as an approximation. So each S sub I can be viewed as an approximation of 1/3. Because, for instance, if you round 1/3, right, to one decimal place, this is what you will get. If you round it to 2 decimal places, this is what you'll get. If you round it to 3, this is what you'll get. So each of these, so each term in the sequence of S's, right, and I'm just using S for sum, right? So each SI can be viewed as an approximation of the number 1/3, right? And the better the approximation, the more 3's I would have to have after the decimal point, right? And we could even plot these. We can even plot them. Right? So let's say here is the magical number 1/3, right? These S values, right, the terms of this sequence, the 0.3, when, let's say when n is equal to 1, my S sub 1 is 0.3. So in fact, yeah, let me go ahead and do this. Right? And then I'm going to draw a horizontal line there. And then I'm going to plot the terms of this sequence, right, for 1, 2, 3, and so forth. And this is just kind of an approximation. But basically, let's say this is 0.3, then this one would be 0.33. It would just be a little bit closer, right? And then similarly, that would be closer, that would be closer, that would be closer, that one would be closer, and so on, right? So again, not only that, but if you look at it from this graphical standpoint now, it looks like the number that we know represents that, or is represented by that repeating non-terminating decimal. It almost seems to be like the limit of these terms, right? Like every time I add another 3 after the decimal point, I get just that much closer to 1/3. But if this is finite, if I only have finitely many 3's after the decimal point, I will never be at 1/3. I can get as close as I want by adding another term here or putting another 3 there, right? And that is kind of the motivation. So let's write down that observation. Right? So as n goes to infinity, the sequence S sub n approaches, right, 1/3. So we can view, so we may view 1/3 as the limit of S sub n as n goes to infinity. So therefore, we can write it like this. Let's use our same wonderful limit notation and say the limit of these terms, right? And each Sn is a finite decimal, right? But if we continue adding more and more digits, or in this case 3's after the decimal point, then we will get closer and closer to our value of 1/3. All right? Okay, so hopefully that idea kind of gives you the sense of, what do we mean by an infinite sum? Well, it's almost like we start with an approximation, and then we make the approximation better and better and better with the hopes that as we continue to add more and more terms, then the sequence of these sums, right, these finite sums, will get closer and closer to a fixed number. All right? So let's introduce a little bit more precise notation and terminology, and then give us a formal definition of what we mean by an infinite series, right? So let S sub n denote the sum of the first n terms of our series, the sum of the first n terms of the series. So with the case of the 0.333, Sn would represent 0.33333, and you'd have n 3's after the decimal place, right? So in general, this is what this S sub n looks like. It's simply the sum of the first n terms. So assuming our summation starts at 1, then the first n terms would be represented like this, right? Which I can write in sigma form, where k would go from 1, not to infinity now, but just up to n, and we're adding up those terms, right? And this is called the nth partial sum of the series. Okay? S sub n is called the nth partial sum of the series. Right? And then the question is now, what happens to this partial sum as n gets larger and larger, right? So if the limit as n approaches infinity of this partial sum exists, and let's give it a name. Now, normally when we talk about a limit, we might use the letter L, but in this context, because we're referring to a sum, I'm going to use S without the subscript. So let's say if this limit exists, say S, right? We say that the series, so that the series converges to S. Right, so our series converges to S. And this is how we write it. So remember what our series is now, is when we add up all infinitely many terms, A sub k. So let me write it down. Provided this limit exists, that's what we define as the sum of this infinite series. So it's defined as the limit as n approaches infinity of S sub n, right? So again, if we continue to add more and more terms, right? And the way we do that is if we can come up with a formulaic expression for S sub n, and then take the limit of that expression as n goes to infinity. If this limit exists, then that is defined as the sum of this series, right? So this is the definition for what it means for an infinite series to converge, right? If S sub n doesn't exist, right, then we say that the series diverges, right? So if the limit as n approaches infinity of S sub n does not exist, right? So there is no number that it approaches, like the 1/3 in our previous example. If there isn't a number that the terms of our partial sum approach as n gets very, very large, we say that the series diverges. Now, again, diverges doesn't necessarily mean go to infinity, right? And to kind of wrap up this little intro video, let's look at an example, kind of an interesting one that really, I think it really embodies how you have to approach infinity in a different way, right? So take a look at this. Right. So consider this series. Suppose we have 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot dot dot, right? Suppose all we're doing, we're having 1 minus 1 plus 1 minus 1 plus 1. The question is, does this converge? Does this series converge? You know, think about it. Kind of the obvious thing you'd say, well, yeah, they would all sort of cancel out, wouldn't they? You know, but the thing is, let's apply this concept of an nth partial sum, and then look at what happens to those partial sums as I continue to add more and more terms. All right. So here are the terms in S sub n. So remember what S sub 1 represents? It would represent the sum of the first one term, right? So it's just the first term there, so that would be 1. S sub 2 would represent the sum of the first two terms. But if I add 1 and negative 1, I'll get 0. Okay? Then S sub 3 represents the sum of the first three terms. So if I take 1 minus 1 plus 1, I'm back at 1 again. S sub 4 is the sum of the first four terms. So then I would have 1 minus 1 plus 1 minus 1. And then I'm back at 0 again. But you see what's happening with these partial sums. As my n gets bigger and bigger, let me do one more time, just in case you've missed the pattern of the first four ones. Let's do the fifth one. So it's 1 minus 1 plus 1 minus 1 plus 1. So now we're back at a positive 1. So here is the sequence. So the sequence S sub n is this. We can list them. I mean, we see the terms, and it's a pretty simple pattern. It's 1, 0, 1, 0, 1, and it just continues like that indefinitely. So then we ask ourselves, do these terms approach a fixed number? No, they don't. They oscillate between 0 and 1, right? So as n goes to infinity, right, so, oh, come on. So as n goes to infinity, S sub n simply oscillates, right? So it oscillates between 0 and 1. It never approaches a fixed number, right? It never approaches a fixed number. Well, what does that mean? It means the series diverges. So therefore, the series, and let's write it back out again. So the 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, and so on, this series diverges. So oftentimes when you think of something being divergent, you think of something, okay, going off to plus or minus infinity, getting arbitrarily large, either in a positive or a negative way. But it doesn't have to be that way. You can have lots of series that they diverge just because of their the property of being oscillatory. Right? So it oscillates between two numbers or maybe several numbers. It doesn't have to be just 2, but as n gets very, very large, the terms never approach a fixed number. Right? So that's kind of the idea behind the infinite series. It's thinking of the series in terms of this partial sum, where we can do the actual addition. See, that's what we were able to do. We were able to do the actual addition and see the pattern in the partial sums, and then that led us to this particular conclusion, right? Because we can't necessarily, right? Now let's say if the pattern were more complicated, maybe it would then be harder to come up with S sub n, right? But that's why we're going to develop some theory and some methods that will allow us, in some instances, to actually find what S sub n is, and then be able to compute its limit. And then others are going to be so complicated that we can't find S sub n, but we will use other information to determine whether or not the series converges or diverges. All right? So I'm sure you're dying to see what all that other stuff is. Well, why don't you tune into the next video, and I'll see you then.